Okay, so I told you that the first two ways we have to make a straight chain ether, these are going to be made by SN2 reactions. But the third way we have to make a straight chain ether, this is going to be by an addition reaction to an alkene. And this is the exact same reaction we saw before in the alkene addition chapter. Okay, the only difference here is that we're going to be adding an alcohol to an alkene this time. Okay, so let's see how this happens. Okay, so let's start out by talking about the goal of this kind of reaction. And the goal of this reaction is just to do a simple addition like we've seen many times before. Think back to our alkenes addition chapter. Remember we had a couple simple additions like adding HBr or HCl or some kind of HX to a double bond. We also did H2O and H2SO4 adding to a double bond. This alcohol addition to an alkene to a double bond is going to behave exactly the same way. Okay, so let's go ahead and write this down, that the goal of this addition of alcohols reaction is to just do a simple addition. Like we saw many times before, such as when we used H2O and H2SO4 to add to a double bond. So for example, when we used H2O and H2SO4 to add to a double bond. Okay, so think back to those addition reactions. This addition of alcohols reaction is going to behave exactly the same way. Okay, so please believe me when I tell you that you already know how to do this reaction if you know how to do this reaction. Okay, so let me prove this to you. Let me take this exact same double bond and let me have this react with water and H2SO4, and you're going to see how similar these two reactions are going to be. Okay, so let me go ahead and add in water and H2SO4. So the only difference here, you guys, is that instead of adding in a water in this reaction, we're adding in an alcohol. But remember, water and alcohol is very, very similar. Water looks like this. Alcohol looks like this. So these have very, very similar properties to each other. They're almost identical. The only difference is that water has a hydrogen on both sides and an alcohol has a hydrogen on one side and an alkyl group on the other. But they should look very, very similar to you guys, okay? Okay, so in the first step of this reaction, we threw in water with an acid catalyst. Why did we throw in an acid catalyst? Why do you ever throw in an acid catalyst? To protonate something, right, you guys? So remember, we had water in here, and you threw in an acid catalyst, H2SO4, which you can abbreviate HOSO3H. Why did we throw in H2SO4? Because we wanted to use it as an acid catalyst to protonate something. What were we protonating back then? This water, right? So this oxygen would go, pick up this hydrogen, kick the electrons to that oxygen, and this would make H3O plus. Remember, you guys, this would make HOH plus, H3O plus. So that's why I told you whenever you add water in with H2SO4, add water in with an acid catalyst, this will protonate water and you will make H3O plus, okay? So the first step in this reaction was water and H2SO4 combining to make H3O plus, which look like this. Let me go ahead and erase this over here. Okay, so adding in water with H2SO4, this acid catalyst will protonate water, turning it into H3O+, putting a positive charge on an oxygen. Oxygen is already pretty electronegative. Putting a positive charge on oxygen makes it even more electronegative, makes it pull even harder on electrons away from its neighbors, away from its neighbors, away from its neighbors. So this oxygen is pulling really hard on these electrons away from each one of these hydrogens, making these hydrogens really electron deficient. Okay, so each one of these hydrogens is saying, I don't have enough electrons. Somebody give me some electrons because oxygen is taking them away from us, right? So let's just take this hydrogen for example. He's saying, hey, I don't have enough electrons. Somebody give me some electrons. So this double bond, these two carbons in this double bond say, hey, we got a lot of electrons in this double bond right here. Maybe we can break this double bond and share those electrons with that hydrogen. And that's exactly what happens here, right, you guys? So these two carbons, they break this double bond. One of the carbons is the one to use these two electrons to pick up this hydrogen. Kick these electrons to this oxygen. And which carbon was it that took it upon himself to break this double bond and use those two electrons to pick up that hydrogen? Was it this carbon on the right that picks up this hydrogen, or was it this carbon on the left that picks up this hydrogen? Well, remember, you always want to do this reaction so that you make the most stable carbocation, right, you guys? So remember, this hydrogen will go on the carbon on the right. It will bond to this carbon on the right, because that will put the carbocation on this carbon on the left. And if you guys don't remember why you want to do that, well, compare it to what would happen if you put the hydrogen on the left side instead. So if instead you thought that this carbon on the left would break the double bond and use those electrons to pick up that hydrogen, and it would get bonded to the carbon on the left, well, that would put the carbocation on this carbon on the right. And you always want to form the most stable carbocation. So if we compare these two options, this is a, what kind of carbocation? Primary, secondary, tertiary? Well, this carbocation is surrounded by 1, 2 carbon groups, so this would be a secondary carbocation, versus this carbocation, which is surrounded by only 1 alkyl group, 1 carbon group, so this would be considered a primary carbocation. So which one would you rather form here? Which one is the more stable carbocation? The more substituted one, the secondary carbocation, is more stable than the primary one. So that's why we're going to have the carbon on the right be the one to break the double bond and use those electrons in that double bond to pick up that hydrogen, right, you guys? Okay, so go ahead and erase this because this is not going to happen because it forms the less stable carbocation. Okay, so remember in an alkene addition reaction, one of these carbons is going to take it upon himself to use these two electrons, break the double bond, and pick up this hydrogen in this case, right? So I always like to imagine this, that one of these carbons is going to swing down these electrons like a drawbridge kind of. So swing this double bond down to pick up the hydrogen, which is how this carbon picked up this hydrogen. By using these two electrons, swing down and pick up that hydrogen, and now you have the hydrogen attached, okay? You also just deprotonated H3O plus, turning it into H2O. Okay, so once you get to this step, this carbon is a carbocation now. It has a positive charge on it. It's really electron deficient. He's saying, whoa, I don't have enough electrons. Somebody please give me some electrons now. Okay, so this water has an oxygen with a lone pair. So this oxygen is like, hey, I got a lone pair. I can come share electrons with you, carbon. Okay, so he goes and shares electrons with this carbon. A carbocation, though, is what hybridization, you guys? It's sp2, which means it's what shape? Trigonal planar, which means it's flat, which means that when this nucleophile comes to attack this, it can attack from either the bottom or from the top, giving you a racemic mixture as long as your compound is chiral. Okay, so just remember a carbocation, this thing is flat, it's trigonal planar, so it can be attacked from either the bottom or from the top, giving you a racemic mixture as long as your compound is chiral. Okay, so this water will come in from either the bottom or the top, adding to this carbocation. Like that. Now you are almost done with this reaction. You just have one more thing to clean up here because you have a positive charge on an oxygen. How do you clean up a positive charge on an oxygen? By deprotonating it, right? So go ahead and come and deprotonate one of these hydrogens off of this oxygen with something that has a lone pair. Hey, you have some more water in your solution that you can use to come and deprotonate this. Okay, so I'm just going to go ahead and use some more water to come and deprotonate this hydrogen. kick the electrons off to that oxygen. And this will finish up this reaction. And this was a simple addition of water to a double bond to make an alcohol. Okay, so we saw this in the alkenes addition chapter. I went through this just now to prove to you that you already know how to do this reaction. As we go through this reaction that adds an alcohol to a double bond, I want you to see how exactly similar this is to this reaction that we've done before, okay? Okay, so the first step in this reaction down here where we had water with H2SO4, we protonated water with our acid catalyst to turn it into H3O+. The exact same thing is going to happen in this reaction up here, except this time we don't have water that's going to get protonated, we have alcohol, our CH3OH that's going to get protonated by our acid catalyst. Okay, so you don't have to write this down if you don't want to, but how this happens is just how water got protonated. So here's CH3OH. I'm just writing it in the reverse direction and you'll see why in just a second. This methanol gets protonated by our H2SO4, which I'm abbreviating HOSO3H there. So this alcohol, this oxygen of this alcohol is going to go and get protonated. It's going to pick up that hydrogen, kick the electrons off to that oxygen, and this is going to make HOCH3H, which is going to put 3 bonds to this oxygen, which is going to put a plus charge on that guy. So this should look very, very similar to H3O+. The only difference here is that we've got a CH3 on this oxygen this time instead of having all hydrogens on that oxygen. Okay, so realize that when you take CH3OH and add it with some acid catalyst, some H2SO4, this is going to protonate this oxygen of the alcohol, turning it into sort of H3O+. Not really, it's going to turn it into a protonated alcohol, but that's very, very similar to H3O+, okay? Okay, so taking CH3OH, adding it in with acid catalyst, this is going to protonate your alcohol and turn this thing into your alcohol, but now in the protonated form, which puts a positive charge on that oxygen. Okay, so hopefully you're starting to believe me that this reaction is going to be very, very similar to this reaction that you already know how to do. So since you already know how to do this reaction, and I'm telling you this reaction is going to behave exactly the same way, I want you guys to hit pause in your DVD player right now and give this reaction a try, okay? So you should already know how to do this reaction. If you're not quite sure, go ahead and refer to this reaction down here to help you get through it. But go ahead and hit pause in your DVD player, give this a try because I know you already know how to do this reaction, okay? And then we'll come back and go through it all together. Okay, so hopefully when you tried this reaction out, you got something similar looking to this. Let's go ahead and do this together now though. Okay, so in our first step, we have our alcohol with our acid catalyst. The acid catalyst will protonate the alcohol, turning it into the protonated form. This is exactly what happened here with water and H2SO4. H2SO4, the acid catalyst, protonated water to turn it into H3O+. Okay, so at this time with H3O+, this oxygen with the positive charge is pulling electrons away from its neighbors because it's really electronegative. So this hydrogen is getting its electrons taken away by oxygen, so it's saying, hey, somebody give me some electrons. These carbons in this double bond say, hey, we've got a lot of electrons in our double bond. Why don't we share those electrons and pick up that hydrogen? So one of these carbons will take it upon himself to swing these electrons down and pick up this hydrogen. We said it's which carbon? The carbon on the right, because it will result in the most stable carbocation, right? So this carbon swings these electrons down, picks up this hydrogen, which is where you see it bonded here. The exact same thing is going to happen up here, you guys. Here you have an oxygen with a positive charge on it. It's pulling really hard on the electrons away from its neighbors, making these neighbors say, hey, I don't have enough electrons. The easiest neighbor to pull off of an oxygen is a hydrogen as opposed to an alkyl group. So this oxygen is pulling electrons away from these hydrogens. So these hydrogens are saying, I don't have enough electrons. Somebody give me some electrons. So these two carbons in this double bond says, hey, we got a lot of electrons in our double bond. Why don't we swing our electrons down and pick up that hydrogen? So one of these carbons, whether the carbon on the left or the carbon on the right, is going to break the double bond, swing down these electrons, and pick up that hydrogen. Which carbon is it though, you guys? The carbon on the left or the carbon on the right? The one on the right. So we have this carbon on the left swing down these electrons to pick up this hydrogen, kick those electrons to that oxygen, so that we get the hydrogen on the right side and the carbocation on the left carbon. Why did we want to do it this way as opposed to having the carbon on the left pick up the hydrogen and putting the carbocation here? Because if we put a carbocation on this carbon, that would be a less substituted, less stable carbocation than when you put it here. Okay, so if you want to, go ahead and give that out a try on your own. Okay. Okay, so in our second step down here, we just picked up this hydrogen to put a positive charge on this carbon, making a carbocation, making it electron deficient. So this carbon's like, I don't have enough electrons, somebody give me some electrons. This oxygen's like, hey, I got a lone pair, I can share with you and be covalently bonded. Carbocations are flat, they're trigonal-planar, so they can be attacked from the bottom or the top. So this water, this oxygen is going to attack from the bottom or the top, attaching this to that carbon. The exact same thing happens up here, you guys. Here you have a positive charge on this carbon now. So this carbon is saying, I don't have enough electrons. Somebody give me some electrons. Here you have an oxygen with some lone pairs. This is going to add to this carbocation from either the bottom or from the top. Since the carbocation is flat, it's trigonal planar, can be attacked from the bottom or the top, giving you a racemic mixture as long as your compound is chiral. Okay, so this oxygen of this alcohol is going to come to attack that carbocation, which is why you see it attached right there. At this point, we said we were almost done with the reaction, except we just had one thing left to clean up. What was that? The positive charge on the oxygen. And how do you get rid of a positive charge on an oxygen? Deprotonate it, right? So we brought in some more water that we had in solution to come and pick off this hydrogen to give this oxygen back its lone pair to cancel out the positive charge. Exact same thing is going to happen up here, you guys. We're almost done with this reaction now, except we just got to clean one thing up. What is it? The positive charge on the oxygen. And how do you clean up a positive charge on an oxygen? Deprotonate it, right? So we're going to take off this hydrogen, and we don't have water in this case, but we have more alcohol, which can behave like water. So we have more alcohol that we can use to come and deprotonate that hydrogen. So I'm going to just use some more alcohol, come and deprotonate this hydrogen, give this oxygen back its lone pair to cancel out the positive charge. And check out what we made here, you guys. We made an ether, an oxygen surrounded by not one, but two alkyl groups. So this is an ether. This was the third way we have to make a straight chain ether, okay? I hope you guys realize that this is not a new reaction. This is going to behave exactly the same way as the other addition reactions we've seen before. Specifically, it behaves exactly like H2O and H2SO4 adding to a alkene, a double bond, okay? Okay, so go ahead and take a moment if you want. Hit pause in your DVD player as soon as I step off screen so you can compare these two reactions step by step by step by step, so you can see exactly how similar these are. They undergo the exact same mechanism, okay? After you get that down, then we can move on to our last way to make an ether, which is our +1 way to make an ether. Okay, so we're finished learning how to make our straight chain ethers. These first three ways, these are how to make straight chain ethers. Our +1 way is going to be how to make a cyclic ether, an ether that's inside a ring. Okay, so go ahead and hit pause in your DVD player, finish getting these first three ways down, then we'll move on to our last way, our +1 way to make a cyclic ether. Okay, so we just finished learning the first three ways to make a straight chain ether. These were the Williamson ether synthesis, the acid-catalyzed dehydration of alcohols reaction, and lastly the addition of alcohols to alkenes reaction. These were three ways to make straight chain ethers. The first two ways we saw, these used SN2 reactions to make an ether, and the third way we saw used an addition reaction to a double bond to make an ether. Now I want to show you the +1 ways to make an ether, and this is going to make a cyclic ether. This is known as an intramolecular reaction to make a cyclic ether. Okay, so we're going to be doing intramolecular reactions to make these cyclic ethers. And what does this mean, intramolecular? This means that we're going to be doing the reaction all inside one molecule. So we're not going to be adding in a bunch of molecules to react together. This reaction is going to occur within one molecule. It's going to react within itself to make a cyclic ether. But believe me when I tell you, you actually already know how to do this reaction also. It's actually just an adapted form of the Williamson ether synthesis. Okay, so remember the Williamson ether synthesis? This is where you take an alkoxide ion and you add it to what? An alkyl halide, right? Like this, for example. This alkoxide ion is going to be the nucleophile. This alkyl halide is going to be the electrophile. This oxygen can come, do an SN2 reaction, attack this carbon, kick off bromine because bromine is a good leaving group, and this join these together in an ether. Okay, so this would be considered an intermolecular reaction. This reaction occurs between two molecules, but for an intramolecular reaction, this is all going to happen within the same molecule. Let me show you what I mean. Okay, so these intramolecular reactions, these can't just happen with any compound. They have to happen with very specific compounds. Let me show you an example of one. Let's take a bromine, a good leaving group that's connected to 1, 2, 3, 4 carbons, and an alcohol. This is a great compound for doing an intramolecular reaction, and you'll see why in just a little bit, okay? But what you should see so far is that you have a bromine, a halogen, a good leaving group, and you also have an alcohol here. Remember you guys, in a Williamson ether synthesis, what you did here was take an alkoxide ion, add that to an alkyl halide, and then do an SN2 reaction to make your ether. Here you have an alcohol that can be deprotonated to turn this into an alkoxide ion. So you have an alkoxide ion and you also have an alkyl halide here, all within one molecule. So this is really convenient. You don't have to add in two separate molecules. You don't have to add in one molecule that has the alkyl halide, one molecule that has the alkoxide. This is all just built into the exact same molecule, okay? So let's go ahead and do a SN2 reaction using this oxygen as the nucleophile and this alkyl halide as the electrophile. But hey, you guys, before we can do this reaction, we have to turn this alcohol into an alkoxide ion nucleophile. So how can we do this, you guys? How can we get rid of this H? We can deprotonate this by adding in a really strong base, such as what? How about sodium hydride, like we saw before, right, you guys? So go ahead and throw in some NaH, sodium hydride. This is a source of H- ions, a really strong base, and this can come and deprotonate this alcohol and turn it into an alkoxide ion nucleophile. Okay, so let's go ahead and draw the results of this deprotonation. There's your 1, 2, 3, 4 carbons connected to your alcohol that just got deprotonated, putting a negative charge on that oxygen. So this oxygen is now a great nucleophile. It's really electron rich. It really wants to share its electrons with someone. this bromine is more electronegative than this carbon, pulling electrons away from this carbon, making this carbon electron deficient. So this carbon's like, hey, somebody give me some electrons. And he's like, hey, oxygen down there in the other side of the compound, can you hook me up with some electrons? And this oxygen's like, sure, let's go ahead and do that. Let's curl up this compound so that I can get closer to you. So this oxygen is going to use one of its lone pairs to come and attack that carbon, shares electrons with that carbon, and kick off this bromine. Let's draw out what the result of this is going to be. Okay, so normally when people do this reaction, they like to do this SN2 reaction, kick off this leaving group, and then imagine how this thing is curling up all at the same time. I don't like doing that because I get confused when too many things are going on in my head at the same time. So what I like to do is, I like to show this SN2 reaction so this oxygen is bonding to this carbon and kicking off this leaving group. And so I will just draw it like this. Okay, so I'll have the exact same compound. This oxygen just used this lone pair to come and bond to this carbon, which is what you saw here. So this just made a bond to this carbon and kicked off the bromine. And once I get to this stage, I know it kind of looks like a half of a broken eggshell or something, but at least when you look at it this way, you can see exactly, hey, here's the bond that was made here, and you just kicked off the leaving group. And once you get to this step, then you can just say, okay, this is curled up into a ring. And how many members are in this ring? Well, let's count them up. 1, 2, 3, 4, 5 members in this ring. And what's the shape of a 5-membered ring? A pentagon, right? So after you get to this stage, you just count up the members in the ring. You say, hey, this is a 5-member ring. That's going to be a pentagon. So go ahead and just say that this is equivalent to a pentagon-shaped ring, because you know that this isn't actually how the ring is going to look like, right? It's actually going to look like a pentagon. So it's going to have 1, 2, 3, 4 carbons in this ring. 1, 2, 3, 4 carbons in this ring, and the 5th member in this ring is your oxygen. And you can say that the bond that you just made between this oxygen and this carbon, that's this oxygen bonded to this carbon, okay? And there's the lone pairs on that oxygen. And you guys can do this either way. I was telling you that normally when people do this reaction, they go straight from here to here. But this is kind of difficult for me to do all in one step, so I like to break it up so I can see exactly what's going on. After I see exactly what's going on, I just count up the members in that ring and I translate it into what that ring is supposed to look like, okay? And awesome, you guys, what did we just form here that has an oxygen with alkyl groups on both sides of it? This is an ether, right? But this isn't just any ether. This is an ether that's inside a ring, right, you guys? So this is going to be called a cyclic ether. And this is a cyclic ether that's part of a 1, 2, 3, 4, 5-membered ring, which brings up my next point. Because I told you that intramolecular reactions can't just happen to any compounds. These compounds have to be very specific. You can only do an intramolecular reaction like this if you're going to be able to form a 5 or a 6-membered ring. Okay, so let's go ahead and write this down. That this reaction will happen if you can form a 5 or a 6-membered ring. Okay, so we were able to do this reaction. We were able to curl this thing up into a ring, do this SN2 reaction to form this because this is a 1, 2, 3, 4, 5-membered ring. So this reaction will happen if you can form either a 5 or a 6-membered ring, because a 5 or a 6-membered ring, this is a favored conformation. If you form like a 3, 4, 7, 8-membered ring, these are not favored because they're unstable. 5 or 6-membered rings are stable enough to form, so this reaction can happen. Okay, so let me go ahead and give you guys a practice problem so you can test out your knowledge of these intramolecular reactions now. Okay, so why don't you guys give these two problems a try? As you can see, these are both compounds that have alcohols and halogens built into these, so both potential nucleophiles and both potential leaving groups here. So go ahead and give these two problems a try, and then we'll come back and do them together. Okay, so in this top reaction, we're going to take this compound and react it with some sodium hydride, some strong base, right? So let's go ahead and draw in our hydride ion, our H-, and this is going to come and deprotonate this alcohol. Okay, so go ahead and draw a curved arrow from this hydride ion to deprotonate that hydrogen, kick the electrons onto that oxygen. You're going to get the exact same compound, except now this oxygen is deprotonated. So it's going to have an extra lone pair with a negative charge on it. We've just turned this alcohol into an alkoxide ion, a great nucleophile. And hey, look what else we have in our compound. We have a halogen connected to an alkyl group, an alkyl halide. So hey, this carbon's getting its electrons taken away from it by this bromine. So this guy's like, I don't have enough electrons. Somebody give me some electrons. Hey, oxygen over there on the other side of the compound, can you hook me up with some electrons? So this oxygen tries to, and he's like, all right, let me try to share these electrons with you. And curl up in a how many membered ring would this be? Well, let's check it out. So this oxygen is trying to do an SN2 reaction on this carbon, kick off the halogen leaving group, and let's look at what we would form. And I'm going to just do this half broken eggshell thing as we did last time. So this oxygen is going to bond to this carbon, and this is going to form a how many membered ring? A 1, 2, 3, 4-membered ring. And hey, you guys, are 4-membered rings favored to form? Can this ring form from this compound right here? No, right, you guys, because in the end, this would have to form a 4-membered ring, and this cannot happen. It's way too unstable, okay, you guys? So this cannot happen. It looks like it might have the potential to, but once you draw out the 4-membered ring here, you realize, oh shoot, I can only make either 5 or 6-membered rings. Anything else is too unstable to form, okay? Okay, so let's take a look at this bottom example now, and here we have the same situation. We have an alkyl halide electrophile on this side of the compound and a potential alkoxide ion nucleophile on this side of the compound. But this isn't an alkoxide ion nucleophile just yet. What do we have to do in order to turn this alcohol into an alkoxide ion? Deprotonate it, right? So that's why we have some sodium hydride in here, some strong base. So go ahead and take your H- hydride ions to go deprotonate this alcohol, kick the electrons to that oxygen to turn it into an alkoxide ion. Okay, so we're going to have the exact same compound here. 1, 2, 3, 4, 5. So the exact same compound, except now this oxygen has an extra lone pair, giving it a negative charge. So once you get to this step, this alkyl halide, this carbon is like, hey, I need some electrons because chlorine's taking it away from me. Somebody give me some electrons. Hey, oxygen on the other side of the compound, can you come over here and bond with me so we can kick off this chlorine? So this oxygen is like, hey, I'll give it a try. So oxygen goes to attack this carbon, kick off the chlorine, and attempts to do an SN2 reaction, right, you guys? So let me go ahead and erase this up here, and we'll draw out the result of this reaction. Okay, so you can choose to try to do this SN2 reaction, kick off this leaving group, and curl this thing up into a ring all in one step, but I like to break it up into simple steps for myself. So I'm just going to do the broken eggshell thing and bond this oxygen directly to this carbon. So I'm going to draw this compound out exactly how it's seen right there. So 1, 2, 3, 4, 5. There's the oxygen. This oxygen just used its lone pair to come bond to this carbon, so it uses lone pair to come bond to this carbon. And here we can clearly see what is bonded to what and how many members are going to be in this ring now that it's curled up. 1, 2, 3, 4, 5, 6. This is going to be a 6-membered ring. So is this a potential ring that can form by an intramolecular reaction with this compound? Yes, right, you guys, because you can form a 5 or a 6-membered ring. 5 or 6-membered rings are favored because they are stable enough to form. Okay, so once you know, hey, this is stable enough to form, go ahead and draw how this ring would actually look like. And a 1, 2, 3, 4, 5, 6-membered ring, what shape is a 6-membered ring in? A hexagon. Okay, so go ahead and draw a hexagon. There's a 6-membered ring, and let's make one of these members in this ring an oxygen. And this oxygen just bonded to a carbon, so if you want, you could draw this bond in blue, saying that this oxygen just bonded to this carbon right there, okay? And awesome, you guys, what did we just make here that has an oxygen with alkyl groups on both sides of it? An ether, right? But this isn't just any ether, this is an ether that's curled up in a ring, also known as a cyclic ether, right? Okay, so we learned 3 ways to make a straight chain ether. We've now just learned the +1 way, which was an intramolecular reaction to make a cyclic ether. We're actually going to carry this method into a later part of this session, but for now, we're done making ether, you guys. We learned the 3+1 ways to make an ether. Now let's move on to what we can do with ethers, what kind of reactions that ethers undergo, okay? Okay, so far we've talked about the general information about ethers. We talked about them being very stable compounds known to be not that reactive. We then went on to talk about ways you can make ethers. Now that you know how to make ethers, let me show you some stuff you can do with ethers now. But this might be kind of a weird concept because didn't we just say that ethers are very stable, they're not that reactive of compounds? Yeah, right, so how are we going to be doing these things with these unreactive compounds? And you guys got me there. Ethers themselves are not that reactive. So if you try to do a reaction with an ether, it's not going to be that successful, okay? But what I'm going to show you how to do is take an unreactive ether, turn it into a more reactive compound, and then do reactions on that more reactive compound. Okay, so this is the first thing I'm going to show you in stuff to do with ethers. Take an ether, turn it into a more reactive compound, and then do reactions like SN1, SN2 substitution reactions on the more reactive compound. Okay. The second thing I'm going to show you in stuff to do with ethers is actually going to be taking advantage of ethers being not that reactive. We're going to be using ethers as things called protecting groups. And we're going to get into all of this later, you guys, but let me just for now tell you that ethers are going to be used as protecting groups, which means they are going to be used to cover up certain parts of your compound to prevent it from reacting. Okay, so when you do a reaction, if you did a reaction to kind of a large compound where your compound has several places that can react, then you don't want all those places on your compound to react. So what you're going to do is take an ether and use it to cover up all the places in your compound that you don't want to react, so that you only get a reaction at the specific place you want a reaction to occur. Okay, so ethers are going to be used as protecting groups to cover up places in a compound that you don't want to react. And they're used to do this because ethers are not reactive. So if you turn these different parts of your compound into ethers, then it's like protecting them from reacting, and you only do a reaction at the place you want to do your reaction at. Okay, so let's go ahead and get into stuff you can do with ethers now. Okay, so the first thing I'm going to show you that you can do with ethers is take an ether and turn it into a more reactive compound so we can do substitution reactions on that more reactive compound, okay? So we're going to go ahead and take an ether, which I'm going to abbreviate R, OR, an oxygen between two alkyl groups. And the reason I'm coloring this O and this R in blue is because we're going to be changing these O and this R into a good leaving group. Okay, so we're going to put a good leaving group onto this alkyl group in place of this OR, okay? Because right now as an ether, this thing is very unreactive. If you take an ether, such as say CH3O, CH3, and you try to do an SN2 reaction on this thing with a nucleophile, so say you try to do a SN2 reaction on this nucleophile and you try to say, okay, oxygen is more electronegative than carbon, it's pulling electrons away from carbon, making this carbon partially positive. Let's have a nucleophile come try to attack this carbon, kick off the OCH3 group. What you're going to get is an OCH3 get kicked off as a leaving group. And it's going to have a negative charge on this oxygen. And hey, you guys, is this a good or a bad leaving group? Doesn't this thing look a lot like OH minus? And didn't we just get through saying that OH minus is a horrible leaving group because it's really, really unstable, it's really reactive, and a good leaving group is something that can be stable on its own? These are not stable on their own, you guys. They have a full negative charge on them on an oxygen. This is very reactive. Okay, so we cannot do this kind of reaction onto an ether. This is why ethers are generally not reactive, because they have such crummy leaving groups attached. So what we're going to be doing is changing this OR group, into a halogen, into a alkyl halide. Okay, so we're going to take this ether and swap out this O and this R group for a halogen, okay? More specifically, a good leaving group, okay? So change your ether to a alkyl group that has a good leaving group attached, all right? Oh, and the point of doing this, you guys, of changing an ether, a compound that has an alkyl group connected to a really crummy leaving group, the point of changing this to an alkyl group that has a good leaving group attached is so we can do an SN1 or an SN2 substitution reaction on this more reactive compound. Okay, so take an unreactive ether, turn it into a more reactive compound like an alkyl halide, so we can do either SN2 or SN1 reactions on this more reactive compound. And depending on the structure of this more reactive compound, we're going to be doing either an SN2 or an SN1, okay? Okay, so I told you that ethers are very stable, very unreactive compounds. So to get them to turn into these more reactive compounds isn't an easy task. In order to turn these unreactive ethers into these more reactive compounds, we have to use very, very strong acid. We have to throw strong acid onto these ethers to get them to turn into these more reactive compounds. Okay, so let me go ahead and write up here that in order to get these unreactive ethers to react, to turn into these more reactive compounds, you have to use very strong acid. So use strong acid. Like HCl, HBr, HI, any of those that you don't want to get in your eye, those are strong acids, okay? So we're going to have to use a strong acid to convert this ether into this alkyl group with a good leaving group on it, this more reactive compound, okay? Okay, so just to clarify something real quick, because the whole goal of doing this, the whole goal of taking an unreactive ether and turning it into a more reactive compound like an alkyl halide, the whole point is to make an alkyl halide so you can do successful substitution reactions with it. Okay, so alkyl halides, these are compounds that can do substitution reactions very easily, very reliably. Okay, and whenever you do a reaction, you want it to be as easy of a reaction as possible. So remember back to our free radicals chapter? The whole point of learning free radicals was because it gave us a way of making alkyl halides. And alkyl halides are great for doing substitution reactions. The same thing is true here. We'd love to do a substitution reaction onto an ether, but ethers aren't very reactive, so they don't do them very easily. So we want to turn this unreactive ether into a compound that can do substitution reactions easily, like an alkyl halide. Okay, you guys? So once you get to your alkyl halide, you can pretty much do whatever SN2, SN1 reaction you want. But one thing I want you to see here, so you don't get confused, is that in order to turn an ether into an alkyl halide or a more reactive compound, you have to substitute a bad leaving group with a good leaving group. And what kind of reaction is going to occur here where you have to substitute this bad leaving group with this good leaving group? A substitution reaction like SN1 or SN2. Okay, so do me a favor and write SN2 or SN1 reaction here. And you're going to be doing a substitution reaction to change this unreactive ether into this more reactive compound. But here's the catch, you guys, because you might be thinking, well, Garrett, if you can do an SN2, SN1 reaction to an ether directly, why do we have to go through all this trouble and change this ether into this more reactive compound and then use this more reactive compound to do a substitution reaction? Well, check this out, you guys. In order to turn an unreactive ether into this reactive compound, it's very, very difficult. You have to use very strong conditions like strong acid. So yes, you are going to be doing an SN2, SN1 substitution reaction to turn this unreactive ether into this more reactive compound, but it's not a very easy, not a very reliable reaction. So that's why you want to turn an unreactive ether into a more reactive compound so you can do a substitution reaction very easily, very successfully with this more reactive compound without having to use such strong conditions all the time, okay? So let me go ahead and show you how we're going to do this now. Okay, so I told you that we want to take an ether that has an OR bad leaving group and we want to get this to leave so that we can stick on a better leaving group, okay? So let's go ahead and just take an ether. Let's take diethyl ether, for example. Okay, so this is an ether, and this looks like this if we write it out in the general form. This is ROR, and what we want to do is we want to get rid of this OR bad leaving group and substitute it for a good leaving group. Okay, so we want to find out some way to get rid of this OR group right here and stick on a better leaving group onto this alkyl group right here. Okay, so how are we going to do this? Well, we're going to take this unreactive ether and throw in some strong acid. Okay, so use some strong acid like HI, HCl, HBr. Okay, use an acid that has a halogen attached, and you're going to see why in just a second. Okay, so I'm going to go ahead and just throw in some HI. And why do we want to do this, you guys? Why do we want to throw in a strong acid? Well, what are we trying to do here, you guys? We're trying to take this bad leaving group and turn it into a good leaving group. So let's see what will happen. If you throw in strong acid, what does acid do? Acid protonates things. So in this reaction, you have an oxygen with a lone pair that can be protonated by this strong acid. So let's have this oxygen pick up this hydrogen, kick the electrons to that iodine, and you're going to protonate this ether. Oxygen now has 1, 2, 3 bonds to it. That's one more bond than it wants to have, so it's going to have a positive charge on that oxygen now. Okay, so what did protonating this ether just do? Well, it put a positive charge on an oxygen, which has two important results. One is that oxygen, does it want to have a positive charge on it? No, right? Oxygen is fairly electronegative, so by putting a positive charge on it, oxygen is going to become even more electronegative. It's going to pull even harder on the electrons away from its carbon neighbors, making this carbon neighbor and this carbon neighbor really electrophilic. So this oxygen is pulling really hard on these electrons. This oxygen is saying, hey, I have a positive charge on me, give me those electrons. Okay, so this oxygen obviously wants to break this bond and take those electrons for himself so he can leave. Okay, so two things happened here. By putting a positive charge on this oxygen, he's pulling really hard on this carbon, making this carbon really electrodeficient, making it a good electrophile. And this also makes this group right here a really good leaving group, because now oxygen wants to take these electrons for itself, break this bond, and leave this compound. And this should look very, very similar to something else we just saw a moment ago. Remember, you guys, when we had an alcohol like this, and we said, how can we turn a bad leaving group like OH into a good leaving group? How did we do that, you guys? Well, we threw in H2SO4 strong acid, protonated this oxygen and turned it into this right here, the protonated alcohol. This put a positive charge on this oxygen, turning this good or this bad leaving group into a great leaving group, turning this bad leaving group OH into a good leaving group H2O. Because remember, you guys, if a nucleophile were to come and attack here, it could attack this carbon, which is now really electrophilic because oxygen is pulling really hard on these electrons away from this carbon. So a nucleophile can come attack this carbon, kick off water as a leaving group. And is water a good or a bad leaving group? Water is an awesome leaving group, right, you guys? It's neutral, it's not reactive. It's the epitome of good leaving groups, okay? So we turn this bad leaving group, OH, into an awesome leaving group, which is water. We're doing the exact same strategy with this ether. We're turning this bad leaving group into a good leaving group by protonating it. So check out what happens here, you guys. By protonating this OH, it turns this whole thing into a great leaving group because it can leave as water. The same thing is true up here. By protonating this, it turns this entire half of the compound into a great leaving group because if a nucleophile were to come and attack this carbon now, it could kick off this alcohol as a great leaving group. Okay, so what would this leaving group look like? It would be an alcohol. And remember, I told you guys, alcohols and water, these are very, very similar. Both of these are going to be great leaving groups, okay? So the same strategy is being applied here to turn this into a good leaving group by protonating it, just like we protonated an alcohol to turn OH, a bad leaving group, into water, which was a good leaving group, okay? Okay, so let me go ahead and clean some of this stuff up here. All I wanted you to see was that we were using the same strategy of turning a bad leaving group into a good leaving group by protonating it. And look how similar these leaving groups are, you guys. Water and alcohol, they both have oxygens connected to a hydrogen. It's just this oxygen down here has a hydrogen connected to it on the right. This oxygen has an alkyl group, but they're very, very similar. They behave very similarly, and so you can kick both of these off as leaving groups. Okay, so let's start this reaction one more time. We're trying to take this ether and turn it into an alkyl halide. And what's the first step towards doing this? Taking this half of the ether, the OR group, and turning this into a good leaving group so we can kick it off and eventually replace it with a halogen to turn it into an alkyl halide. Okay, so how do we kick this off as a good leaving group? By protonating it, right? You guys, that's why we throw in strong acid like HI. So there's your HI, strong acid. This is in here to protonate something, and it's going to protonate this oxygen. So have oxygen pick up that hydrogen, kick the electrons to that iodine. And you've now just protonated this ether, putting a positive charge on this oxygen, turning the carbon neighbors into electrophiles because oxygen doesn't want to have a positive charge on it, so it's pulling really hard on its carbon neighbors, making them electron deficient, making them electrophiles. It's also turned this bad leaving group into an awesome leaving group because this can now leave as an alcohol, as a neutral alcohol that looks like water. Okay, so we just picked up this hydrogen, kicked off this iodine, so we also have an iodine in here. And we've turned this into an awesome leaving group. This thing is ready to leave. This oxygen wants to break this bond so it can get its lone pair back and cancel out that positive charge. So hey, you guys, what can come in to attack this carbon to kick off this as a leaving group? How about this iodine with all these lone pairs right here? So this iodine is going to use one of its lone pairs to come and attack this carbon and kick off this leaving group. In a what kind of reaction? This is an SN2 reaction, simultaneous bond making, bond breaking. And this can be done because this carbon electrophile is unhindered. It doesn't have a lot of stuff in the way, so it can do an SN2 reaction very easily. So here's these two carbons right here, and this iodine just attached to this carbon right here. and you kicked off this as your alcohol leaving group. So you can just draw this up here somewhere. And awesome, you guys, what did we just make here? An alkyl halide, a carbon with a halogen attached, which is what we were trying to do. We were trying to take an unreactive ether, something that can't do SN2, SN1 reactions very well. We wanted to turn this into an alkyl halide, something that can do SN2, SN1 reactions very easily. Okay, so we've now made this into our alkyl halide. We've made this into our compound with a good leaving group. Now you can use this to do either SN2 or SN1 reactions. Okay, so after you make your alkyl halide, you can go ahead and just store this in your flask until you're ready to use it, and then you can use it in whatever SN2, SN1 reaction that you want, okay? But the thing is, when you